algorithms. Any questions so far?
So when you say selected, I mean, so there's another 864221 floating around with different numbers selected? Is there?
For instance, for the same partition, we can choose one of the twos.
Okay.
But that will give you another exponent for A. Even if you select 3 parts, that would be another contribution to the same coefficient. You don't have to, there is no imposed selection process.
Okay, it's all possible selections.
Yeah,
independent.
The only requirement is that they have to be distinct. Right, any other questions? Okay, the next, one of the next easiest results in partition theory or Q-series is the so-called q-Gauss summation. It has more parameters in it. And that's our goal. We will try to give a bijective proof to q-Gauss summation. Let's state the result first. Again, it asserts the identity between a series and an infinite product. And j greater than or equal to 0, there are many different formulations, but we will stick to one of them. We have minus a sub j times minus b sub j times c times q divided by a times b raised to j, and downstairs we have q sub j and c times q sub j. This thing equals the infinite product minus cq over a sub infinity minus cq over b sub infinity divided by cq sub infinity times cq over ab sub infinity. If you compare it with binomial theorem, instead of one such list, we have 2 such lists. One is coming from here, the other is coming from there. There's a bijective proof of this fact by Ae Ja Yee. That was a solved paper back in 2004. Well, if we had a bijection before, why did we do it again? I'll come back to this question. Anyway, I don't think I have time to go over all details of the proof, but I'm trying to show you some highlights. So we got the initial idea from algorithm Z.
So the first bijective proof was by Ae Ja Yee in 2004?
Yes.
So it's not a classical identity.
Yeah, that's a very classical result, and it has like tons of different proofs.
And there were no bijective proof before?
I don't think so. I mean, we haven't come by it.
Yeah. And you have a better one now.
Let's not say better,
They're
but
different.
it has potential to go in the direction we want. Ae Ja Yee's proof didn't go in that direction, didn't generalize in that direction. So in algorithm Z, we can look at the following staircase. So we have 6 steps here, 0, 1, 2, 3, 4, 5, and in the previous example, we selected the first, the third, and the fourth one. We can regard this as a rigid shape. The corresponding problem in q-Gauss summation is interpretation of these two factors on top. we can interpret this thing easily, that thing and that thing. We will have some preliminary pair of lists, but then it comes to interpreting those two factors. We have two staircases, one coming from these A's and another coming from B's. So we have 2J places, no, 2J steps. So for j equals 6, we have two copies of this thing. So we have 12 steps. But when j equals 6, you have exactly 6 places to fit them. So both the forward phase and the backward phase, they have to be explained separately. The forward phase is not as obvious as algorithm Z, because as I said, you could have this rigid shape, every step has a fixed position, but in this case you have to play around with those steps. For instance, if you have few enough A's and B's, for instance, when you have less than 6 steps, you can fit them. Here's how we do that. Suppose that you have chosen A to 0, A to 1, and B to 2. A equals 0, A to 0 would go in the first position. 6 positions. If you have pure A's but no B's, you just repeat algorithm Z. But if you have a hybrid of A's and B's, here's what you do. Whenever you pass from A to A, you increase the size of the step by 1. Whenever you switch from A to B in this direction, you don't change the number. So the next thing would be B to 1. But we want B squared. So we go one more step and write B squared there. If we had A cubed, that followed it, again, passing from B's to A's, you increase by 1, and you would write A cubed there. Compare it with B squared by itself, just B squared. That will be placed in the third position, because B to 0, B to 1, B squared. So we don't have that rigidity anymore. Things can move around. Plus, another problem is if you have too many A's and B's, you have to combine some of them. Again, I'm going to work on an example. Suppose that j equals 6, and we have the following steps. Let's say A to 0, A squared. We have to leave one space in between because A to 1 would go there. And after A squared, we had B squared that could immediately follow A squared. Remember, switching from A to B's, we don't change the size of the step. And after that, suppose that we have A cubed and B cubed. And after that, we have A to 5 and B to 5. Again, we leave one space because this would be reserved for A to 4 or B to 4. How many spaces did we use? We use 1, 2, 3, 4, 5, 6, 7, 8, 9 spaces. But we have to fit these in 6 spaces. And here is the sort of comparison. I'll try to explain the magic in a moment. Okay. Now we have fit the thing into 6 spaces, and if you count the number of boxes, they match. The rightmost one will be labeled AB, not just A or just B. It's going to be labeled AB. Same for the fourth one from the right, and the first one is going to be labeled A. The fifth one is again A. The last one is B. Now let's try to see which box went where. This B here, 5 boxes is here. Its companion, 8 to 5, is fit there. And we combine their labels. And whenever we have a hybrid label, A times B, we make sure that we have exactly 5 boxes down. J equals 6, J minus 1 equals 5. And from that point onwards, we use recursion, or if you like, induction. Once you get rid of these two things, then the number of places you can use is reduced by 1, so J equals 5 now. And J minus 1 would be 4. But still, you have 5 places there. 1, 2, 3, 4, 5, 6 things to fit in. We do the following. These 4 boxes come from these 2, and its companion is that one. And their labels are combined, A times B. And finally, we have 4 spaces left, and if you rewrite these things, now you have A to 0. Well, that's not A to 0, in fact, that's only one A, but Q to 0 together with that. This is A together with Q squared now, that's B together with Q squared. Let's say A2, B2, and these are the ones you see there. So that's more or less how the forward phase goes. If you require too many spaces, just condense the parts, and there is a way to do that. There is a proven algorithm. There is a clear-cut algorithm, but it's just messy. So I'm not gonna go over the details. Do I make some sense at this point?
So once again, what is the input, what output? You start from the right-hand side,
Yeah, that's the input.
so it's pairs of,
That's gonna be the output.
okay.
And
The output corresponds to the left-hand side?
yeah, output. We were talking about these 2 factors only. So we fit these boxes under the contribution coming from these two guys, and that's going to give us a separate list. Yeah, so this is the forward phase of the algorithm, and for the backward phase, let's work on an example here, and I'm gonna cut it short. Okay. Given the following parts, that's labeled B, 9, that's labeled A, another 9, that's labeled A times B, and there's a 6, which is labeled C, there's a 4, which is labeled A, and there's another 4, which is labeled C. Is not labeled at all, and the 6 is labeled A times B. Now we are good. Okay. Now we'll try to see how to decompose these things. Now for the unlabeled part, we don't care about that. We collect all the pure labels on the right. The pure labels are A, and B. We collect them all the way to the right. So we would have 11 here, 9 here, and 4. 4 is labeled A, 9 is labeled A, 11 is labeled B, and we would have this unlabeled part in the middle, and we collect all the hybrid labels on the left. So there are 2 of them, 9 and 6. Okay. After we do this, per our agreement, the rightmost A would have contribution 0. The next one, we switched from A to A, so it will have 1 more contribution. The next one, we switched from A to B, that would have the same contribution. So we don't increase. They will decrease the other numbers, 10, 8, and 4 there. And whenever we have a hybrid label, the contribution is exactly 1 less than the number of parts. We have 6 parts, so this would be 1 plus 5, that would be 4 plus 5. Now, we forgot something.
The 4 with empty label?
Oh, sorry about that. Yeah. There is a 4 here. Let's say 0. Okay. These pure labeled parts would be moved according to algorithm Z. When you move them 1 unit to the left, they would be, the top one will be decreased by 1, the bottom number will be increased by 1. But the big deal is how to move these hybrid labels around. For instance, we want to move this 1, we want to swap these because 4 is not in the correct place, we still move that. But since the contribution has to be 5, we cannot do anything to these two. So we decrease 4 by 1. That's where these horizontal set of boxes come from. And that's the only thing you need to do. In addition, you move these hybrid labels according to this rule. So apparently, you have to move the first one all the way to the right so that the number will be in its proper place. Well, 1 would be less than or equal to everything, so this has to come all the way to the right. And it seems that this part is okay if we move it twice to the right, and for the remaining parts, you continue as you do in algorithm Z. So this thing proves q-Gauss summation bijectively. There is a way to go back. I mean, from the, oh, that was part of the backward algorithm. There is one more detail how to tell which J you are looking at, because you don't have a single list anymore. You have two lists. But instead of talking about that detail, I will move on to what we want to do next. Any questions at this point? Okay. Now back to the question, if this was done before, why did we do it again? We wanted to prove the finite version of q-Gauss summation, which is known as q-Celsius summation. Again, that has many different versions. We will stick to one of them. This time we have a finite sum on the left. Say from j equals 0 to n. And choose j where the q-binomial coefficient is defined as q sub n divided by q sub j times q sub n minus j. And the quotient here is scarier. Minus a sub j, b sub j, cq over ab. That quantity raised to j. And downstairs we have cq sub j and cq over ab times q to n minus j sub j. This is called, well, okay, I didn't give you the right answer. Same factors, excuse me, same parameters, except that these are finite products. When you take the limit as n goes to infinity, you get the q-Gauss summation. That was our goal, but we had to make a pit stop at q-Gauss summation because this algorithm didn't generalize in the way we wanted. So we first went over Ae Ja Yee's previous method. It failed, and we tried this thing. We managed to prove q-Gauss summation once again bijectively, but this either didn't generalize yet. So we are still working on this. This is a work in progress. And I have a handout for you. Please pass this around, then I'm going to explain that to you. The way we prove this, we sorted out counterexamples. We began with j equals 0, nothing to prove there. J equals 1, almost trivial. J equals 2, everything fit into place, but we didn't have any explanations. J equals 3, we had 50% of the algorithm. J equals 4, we had 75%. And we thought that if it goes on like this, we will have part and part of the proof, but not the whole one. Fortunately, when J equals 5, after a couple of hundreds of examples, we completely understood what's going on. Fortunately, we have some very unpleasant counterexamples for this finite version. So algorithm Z works fine with finite versions of some identities, but this new thing doesn't work that nicely. And the handout I gave you is the part of the hand-generated
Experimental mathematics.
What's that?
Experimental mathematics.
Yeah. So they were experimental, and even the examples are hard to generate by hand for the finite version. So we wrote a computer program. We had pages of examples to look at, and it's taking time. And this is where I'll stop. Thank you for your attention.
So this is still a work in progress. You don't have a bijective proof for this.
Not yet. I mean, people may have tried that under certain, let's say, spatial choice of parameters, but not the general one.
I'm curious, many years ago I had a proof also of q-particle status, but not in this formulation. The commentator one, I wanted the negation based on the Fuata.
Yes, I saw that, but I haven't gone over the algorithm.
Yeah, but this is completely different formulation. So
Yeah, this is
this is
a
for
different
distance theory,
formulation.
rather you
Yeah.
something else, words, cutting words,
Okay.
major index. So yeah, I'm curious, any
Oh,
connection.
major indices come into play here.
Ah,
Yeah. Major indices even come into play in q-Gauss summation. Yeah.
any questions? I think I get it here.